Here by going over an example. And this is an example in your book, and I encourage you to open your book and work along with me. This is example 1.3 in your textbook. And we're going to do this example. As we'll do all of our examples and our homeworks, using the methodology given on pages 29 and 30 of the book. So briefly look at that methodology. We're going to follow that now to work through our example. So let me read the example. So we have a lone conducting rod of diameter D and electrical resistance per unit length R prime sub E, and it's initially in thermal equilibrium with the ambient air and its surroundings. So it mentioned ambient air and it mentioned surroundings. So immediately you should start thinking of ambient air, convection, surroundings, radiation. This equilibrium is disturbed when electrical current I is passed through the rod. We want to develop an equation that can be used to compute the variation of the rod temperature with time during passage of the current. So I want to go back now and reiterate our learning goals. So learning goal A, identify and state correctly heat transfer problems. B, learn to make good assumptions and justify and check them. And C, learn to solve real problems with rigorous analysis, applying the rate equations and energy balance, and from your fundamental understanding of the concepts. So let's start with the methodology given on page 29 and 30 of your book, because basically this methodology works you through the learning goals. That's why I encourage you to follow it. So what do we know? So we're going to write down what's known, and this basically is identifying correctly the heat transfer problem. So we know that we have the temp of the rod, and this rod has a diameter D. Changes with time due to electrical heating. And we want to find a relation for the temp change with time. All right, so we know electrical heating's occurred. So immediately we should be thinking of how do we represent that in terms of the energy balance and or rate equation. So electrical heating would be a volumetric quantity. If you're heating this rod that has a resistance that's uniform across its volume, it's going to heat uniformly. So that's a generation term. So that would be the energy that's generated in our energy balance. So the next thing we're going to do is draw a schematic. The book already has a schematic. If you want to draw your own, I'll let you do that yourself. And now on to our second learning goal, assumptions. So what assumptions are we going to make about this? So we need to assume, and it probably would be good to assume if the rod is made of a metal, that the rod temperature is uniform at any time t. So 1, the rod temp is uniform at any time t. Number 2, that the properties are constant. And we make this assumption because properties in this problem probably could have a weak temperature dependence, but within the range of the problem, it's good to make this assumption that they're constant. So constant properties, it simplifies the problem for us. And frankly, we wouldn't learn in this class. We don't have enough time, the type of analysis that it would take to deal with properties that are changing like they can in real life. We may introduce some of that later on, but for the most part, we're going to be making assumptions about properties being constant. And the last assumption we'll make is that we can treat the rod as a small object. As a small object in a large enclosure. Now that one may not be clear to you. Why do we make that assumption? Well, let me talk in general about the assumptions that we make and how you can make good assumptions yourself or learn to make them. In order to make good assumptions, you have to really correctly define the heat transfer problem, and you have to see the relevant modes of heat transfer in the problem. So when we read the problem statement, it kind of gave us some hints. It talked about this rod being exposed to an ambient temperature. It talked about it being exposed to surroundings. And it talked about heating of the rod electrically. So those three things gave us the hint of the ambient temperature says that we're going to have some sort of convection to this ambient. Being exposed to surroundings, the fact that the problem even mentioned it, means that we'll have some radiation exchange with our surroundings. And then the fact that we have electrical heating means that we're going to have some sort of energy generation in the rod. So we make this third assumption here, the rod is a small object in a large enclosure, to simplify the radiation calculation. And you have to take my word for that right now, because I'm not going to go into too much detail until we get to the section on radiation. But we do that to simplify the radiation problem. So now let's move on to the analysis. So the analysis is the last learning goal of this course. To be able to make an analysis, a rigorous one, that's accurate, using all of the heat transfer rate equations, correlations that we'll develop later on, and so on. But also to be able to do an analysis of the problem based on an understanding of the physics, the heat transfer physics in the problem. So today we're going to work with doing a rigorous analysis, and then at the end we'll talk a little bit about some of the fundamental principles so that you can get a better understanding of that. So the first thing we're going to do, and I suggest doing this for all problems, is to start with an energy balance, basically applying the first law. So we have our control volume, and we know that for a generic control volume, we have energy going in minus energy going out, plus the energy that's generated equals the energy that's stored. Energy in minus energy out plus energy generated equals energy stored. So for this